All right, so what we're going to look at is some applications of stationary points. We start with this very random thing on similar triangles. Okay, so similar triangles have corresponding angles of the same size. Similar triangles have corresponding side lengths all in the same proportion. Right, so if this, say, is 5 and this is 2, okay, and these two are similar, then let's say that this one is 10, this one will be 4 because they're going to grow in the same proportion. Okay, so we say that these two triangles are similar, okay, and that's the mathematical symbol for similar there. I think it's tilde, is the symbol there. So let's use that knowledge to answer this famous methods question here from 2010 exam 1, which became affectionately known as the cone of death. So look it up on ATAR notes or something like that and you'll see a bunch of method students there lamenting their performance in this question. Okay, so here we go. We've got a cylinder fits in exactly in a right circular cone. Okay, so that the base of the cone and one end of the cylinder are in the same place as shown in the diagram below. Okay, so bottom of the cylinder. Cylinder is on the bottom of the cone, basically. The height of the cone is 5 centimeters. Radius of the cone is 2 centimeters. The radius of the cylinder is R and the height of the cylinder is H. Now, what we need to do is find H in terms of R. And again, if you don't know this move or you're sort of not familiar with this question is near on impossible to answer, in my opinion. So here's the kind of thing that we want to know. So what I'm going to do is imagine like this as a triangle. So I'm going to imagine drawing a triangle here inside the cone. So that triangle effectively is going to look like this. And we know the measurements of that. That's going to be 5 and that's going to be 2. Okay, it's a right angle triangle. And this, I don't know, it's whatever, it's theta. This angle here, it's theta. Now, we need to get, for this move to work, we need to draw out a second triangle. And the second triangle is going to be, now I know that this is a curved surface here, but if you imagine looking at it, it's going to be flat, okay? And what happens here is we're going to be able to get another triangle out of this, okay? So I'm going to draw that one as well. So imagine like a smaller triangle sitting on the top of this cylinder, making up the distance from the top or the bottom of the cylinder, whichever way you want to imagine it, all the way down to the tip of the cone, okay? Now, this distance here, so this is the one I'm talking about, which is the same as this here, that's the radius of the cylinder. Now what we need to do is we need to grab the height, okay, that's this part here. Well, let's just say that this here is the height of the cylinder, this distance here. Then this part only, or this part here, is actually going to be 5 remove this h. 5 take h. All right, so I know that that one there is 5 take away h to give us this particular distance here, because I'm essentially removing this part from the 5, leaving us with this. All right, now believe it or not, I've got enough information now to do h in terms of r, because I know that these triangles have the same angle and the side lengths are going to be in proportion. They are similar triangles. So what I know is if I compare the sides, so let's just say I'm looking at the ratio between this side and this side, which is 5 on 2, I can write that. It must be in the same ratio as these two together. So let's do 5 take h over r. Okay, you could also do them in reverse. You could have 2 over 5 is equal to r over 5 take h. If you wanted to, it would come out exactly the same. All right, and notice how we've got two variables here and we need to find h in terms of r, i.e. make h the subject. So I'm going to say that this is 5r over 2 is equal to 5 take h. 5r is equal to 10 take 2h. 5r take away 10 is equal to negative 2h. h is equal to, I'm going to divide both sides by 2, so negative 10 divided by 2 is 5. Take away 5r on 2. All right, so we've successfully found h in terms of r. Okay, so I'm a little surprised maybe that this wasn't a show that question, but I think it was probably the last question from the exam that year, and yeah, so most students wouldn't have got any marks from here onwards, because if we have a look at question 2, it says the total surface area S centimeters squared of a cylinder of height h and radius r is given by this. They want us to find S in terms of r. Now the problem is we've got an h in here, okay, and we're not allowed to have that. When it says S in terms of r, it means S is going to be the subject, and the only other variable that's going to be included here on the right hand side is r. We're not allowed to have anything else. Now how do we get rid of that h? Well, we conveniently in the previous problem found out that h was 5 take away 5r on 2. So what we're going to do is substitute for h, and what will happen is it'll be in terms of r only. Let's do it. S equals 2r brackets, 2 pi r rather, brackets 5 take 5r on 2 plus 2 pi r squared. That's probably enough to get us a mark at this point here, but I'm going to expand this out because it just looks like I just feel like I've got to tidy up after myself. I've got 10 pi r on the expansion, take away 10 pi r squared on 2, which would have been negative 5, but anyway, it doesn't matter. 2 pi r squared. Let's rewrite this as 10 pi r take away 5 pi r squared plus 2 pi r squared, and we'll just collect those two up and say that S is equal to 10 pi r take away 3 pi r squared. All right, now did I have to do that? Probably not, don't know. I think I would do it. But if you have a look here, what we're going to do is find the value of r for which S is a maximum, okay? And essentially what we're going to have to do is derive this thing or derive this thing. So we would have had to do this anyway. So let's do the derivative. So we're going to say that, let S equal f of r equals 10 pi r take 3 pi r squared so that I can use some function notation. Let's find f dash r equals, this is going to be 10 pi take away 6 pi r, and the maximum is going to occur when this is equal to 0. 0 equals 10 pi take 6 pi r, negative 10 pi equals negative 6 pi r. R is equal to negative 10 pi over negative 6 pi. They cancel out. R is equal to 5 on 3. Find the value of R for which S is a maximum. So we've only got one value of R because it's this thing here is a parabola, okay, and it's when R is equal to 5 on 3. And what kind of parabola? It's going to be an upright parabola. So that's the value of R, 5 on 3, for which it's a maximum, okay? So there is, and do we need to find what that max value is? Find the value of R? No, that's all we have to do. So that would have got us the 2 marks there. So there is the famous cone of death question, and as I said, impossible if you couldn't do part A. Well, I think anyway. I can't think of any other way to do the problem. All right, so let's go back, and now this looks fairly easy when we compare to what we've just done. So we're going to just have a quick look at stationary points. All right, so there are 3 stationary points on the graph below. Tangents are parallel to the x-axis at these points here. And what we've got here, this one here is a max. This one here is a SPOI, as Ms. Cowan calls it, or a stationary point of inflection. And this one here is a min. Now we're going to note that this is, let's call this a local max, and let's call this a local min. The reason we call it local is it's actually not the maximum value, okay? It's the local maximum or the maximum in this vicinity, but actually what this function I'm predicting will do is continue to increase there to generate a maximum value of positive infinity. So this is a local max. Now same with the min over here, we're going to call this a local min because I'm presuming that this function here will continue off in that direction, which means our actual minimum or our absolute minimum is going to be negative infinity. So this locally is the minimum value, this stationary point. Okay, so let's really get into the habit of calling these the local max, stationary point of inflection is fine, and local min, not just the min. All right, so we've got a particle moving in a straight line and its position is this, where t is equal between 0 and 5. We want to find out when it's furthest away from the origin, i.e. probably the turning point. So we're going to say x is equal to 2t, t plus 5. T is equal to 0, t is equal to negative 5. Okay, so I feel like there's something wrong there. 2t squared, 10t. No, it's good. Okay, so what's going to happen is we've got an upright parabola. It's going to go through negative 5 and keep increasing. So interestingly, this is not one where the stationary point of is included. So I'm going to say sub x equal 5 in, and we're going to say not x equals 5, t equals 5. X is equal to 2 times 5 squared is 25, plus 5 times 10 is 50, which is equal to 100. So that's the maximum distance from the origin. Now, why is this question here in stationary points? Well, in fact, those of you who fall in love with calculus and do dx, dt is equal to 4t plus 10. Find out where the stationary point is. What you're not going to get is the maximum distance, and I'll show you what I mean there. So it's going to be 4t plus 10. Negative 10 on 4 is equal to t. So there is a stationary point at t equals negative 4 on 10. But if I sub that value in, this negative value here, let's just quickly do it. I'm going to define f of x equals 2x squared plus 10x. And if I do f of negative 10 on 4, it's going to be negative 12.5, okay? And what I know straight away is that if that's negative 12.5, and this one here relates to 100, 100 is much further away than negative 12.5. So, like calculus, okay, but don't fall in love with calculus. Okay, so be careful here because those of you who see stationary points and know calculus will just want to throw it at everything. Okay, but in this case, it's simply f of 5 will give you the furthest point. All right, another application of stationary points. So we've got a curve with this equation and it passes through the point 0, 7. It's got a stationary point at 1, 6. And we've got 1, 2, 3 unknowns. Well, 2 unknowns because this is the y-intercept. So we're going to say straight away that c is equal to 7 and rewrite our function. Y equals x cubed plus ax squared plus bx plus 7. All right, now it has a stationary point at 1, 6. So I'm going to sub 1, 6 in. So that's going to be 6 equals 1 plus a plus b plus 7, Let's tidy it up a little bit and say that this is going to be, so 1 and 7 is 8. This is negative 2 equals a plus b. Now, what else do we know? It has a stationary point. That means that for the derivative, when x is equal to 1, y is going to equal 0 for dy dx. So let's get dy dx. It's going to equal 3x squared plus 2ax plus b. 0 equals 3 plus 2 times 1 is 2a plus b. This is going to be negative 3 equals 2a plus b. Now let's eliminate, so this, we'll call that 1, we'll call that 2, and we're going to do 1 take 2 or 2 take 1, it doesn't really matter. B take B is 0, 2a take a is a, negative 3 subtract negative 2 is negative 1. So a is equal to negative 1. And let's sub that into this first one here. So negative 2 equals negative 1 plus b. Add 1 to both sides. B is also evidently negative 1. So b is equal to negative 1. There's our 3 unknowns found. All right. And there is the 10C exercise.